And hello, welcome back to this video on radiation transport. So we are doing our radiation heat transfer learning journal again, and we left off at the moment method. We talked about the first and the zeroth moment respectively, or zeroth and first moment respectively, and talked about the moment method. And so we were saying how can we simplify this equation. So we have this term over here, which is annoying. So we want to define some other form of moment. Okay, we want to define some other form of moment such that we can simplify this term here. So I1 is the first moment defined as such. Now of course there's a differential with respect to tau lambda, which is the optical thickness. Alright, so how is this related to this over here? Okay, so quite straightforward. Whatever you see here is just di1 d lambda. Okay, di1 d lambda. Let me bring leaks out. Okay, so I can just type formulas here. Okay, Control Shift M. Okay, di lambda. Okay, or let me get partial instead. Partial I. Okay, fraction, right? Partial I lambda. Okay, partial tau lambda. Okay, I think I typoed there. Let me correct that typo. Alright, there you go. So I'm looking for di1. Okay, di1. Let's do a di1, and that is equals to fraction partial, okay, by partial lambda or partial tau lambda. Okay, first is 2 pi, which we can just bring out. Then we have the integral from -1, okay, to 1 of what? Mu I lambda I lambda tau lambda. Let's see whether I can zoom in. Yeah, I can zoom in. Okay, very good. Okay, and let me have a d mu outside and close this up. And that is basically what we have here. Notice, let's copy and paste. And we can just bring this 2 pi out because that's just a constant. Okay, so what else is constant with respect to tau lambda? Actually, if you noticed, this whole mu here is actually constant with respect to tau lambda. So the thing is that you can just bring this differential operator in here, and it will be okay. So now what do we have? Okay, we have looking at this here. Okay, we have this is actually di1 d tau lambda, and okay, this is di1 d tau lambda. Alright, this di1 d tau lambda, and this is by definition of it, but we see we can actually bring the 2 pi out, and we can bring the differential operator in. So we find that di1 d tau lambda is actually equals to this term over here. So the I1 d tau lambda is actually equals to this whole term over here, and therefore we can just replace this term on the left hand side with the I1 d tau lambda, because you can switch around we can bring the differential operator inside the integral. So that's how we get this. Of course, I can always export as a plain LaTeX. I'll get the code, overwrite, and let's see. I'm gonna get this text file, display, and let's view the PDF, quick build, and view PDF. Okay, so let's get that out. This is the equation I want, which I can just bring it over. Okay, and I'll just paste it here. Okay, that should do it. I'll do a quick build and a view PDF. Okay, so this is what I actually noted here for you. Basically, it's the same thing. You can just bring the integral inside. Alright. And that actually solves a lot of the problem. Okay, maybe I'll just insert this step. Okay, now I won't insert this step. I already showed you that. Okay, so next thing is once we do that, we need to deal with the scattering term, or not just the scattering term, this term here, the emission term in the medium. So what we see is that this is actually independent of mu, and depending on your scattering, I mean, you can have anisotropic scattering, but if or what? Hey, no, there's no need to for that. This is actually independent of mu. So we can just bring the integral out because both of these are constant with respect to mu. So don't really need to bother too much. This is pretty straightforward. So 2 will just be popping up in front here. The last step is to sort out the phase function here. Okay, so part 1 of solving the phase function is actually integrating out the mu terms. So if we see here, the what we have here is this I lambda term. Okay, this I lambda term and this phase function. Now this phase function doesn't really depend on mu at all, though it has this mu term over here. So this phase function is just there to say, okay, or rather, we can make the assumption to simplify that this phase function does not depend on mu. So that's a simplifying assumption that we are making here. So you got to take note that we assume here that this phase function doesn't depend on mu. One example is, of course, the very simple isotropic case where the phase function everywhere is just the same. Okay, so that's one way of thinking about it. So this assumption here applies like for isotropic scattering, for example. So if this is isotropic scattering, then okay, we can carry on and integrate this with respect to mu I, and take this out of the integral inside. Okay, take this out of the integral inside, and yeah, just get this I lambda out, and we get I naught outside, the zeroth moment. Okay, so after that, it's pretty simple. This thing evaluated with respect to mu I, we know that if we integrate the phase function over 4 pi, we will get this. So if we apply the azimuthal symmetry, we can say that half of this integral of phase function with respect to d mu I equals 1. So substituting that in, okay, I'm skipping a lot of the derivation here from the 4 pi solid angle, but to here, but I roughly explain the concept. How do we get there? So we go from here to here is, after applying, our azimuthal symmetry. And so, yeah, this is what we have. This is what we have. We have this effect happening, and we can actually just simplify this whole term to I naught and omega lambda. Now that's very simple now, and then we can just factorize this out. So this one is just tidying up the radiation transport equation until we get this form over here, where partial of I1 with respect to tau lambda is equals to 4 pi. This is the black body term, and then this is the absorption term. Okay, and you kind of factor in the scattering there. It's just a very neat and compact form. Now, what do we do with this? Okay, well, of course we can get back our intensity fields if you want from this equation. In theory, I think you can do that. But what is more important, of course, you want to calculate heat flux when it comes to radiation. You're not really interested in anything else other than heat flux and maybe G, which is the sum of all incoming radiation over all solid angles. That is G. So just skip this part. And okay, yeah. So that is assuming we solve this equation. However, there are two scalars here. Okay, this I1 and I0, this first and zeroth moment, these are scalars, so they are much easier to deal with than, say, you have your integral differential equation. But since you have these two scalars, you have two unknowns and one differential equation. You need at least one more equation to actually solve this in I1 and 0. So where do we get our extra equations from? So that we can take a look. So you need more equations. We need more equations to help us solve this equation. So what we do is that we repeat this integration process here, which is what we did before. We also integrate out the angles. However, we multiply in mu first. So we multiply mu into all of these equations here, and we repeat the process again. And like before, we define I2. Remember I said I2 is the second moment. This is a second intensity moment where we have mu squared inserted inside. So we define I2, and of course this is the general formula. Ik equals to 2 pi integral blah blah blah. Then you have this mu k inside. So we are going to, let's first get the easy bits out of the way. First is this last term here. I'm sorry, this is kind of spilling off the page. But this one comes out first. I lambda tau lambda mu d mu. This is actually the first moment, which we will see on the right hand side. The second moment will be on this end over here. And we repeat the whole process again. Firstly over here, this term here, we can get this term out. I minus 1 minus omega, the bracket, then IB lambda, and we kind of get this term here to just kind of drop out, because if you integrate this term like this, you will see that it just drops to 0, which is quite interesting. Okay, so that makes it easy because this whole term actually becomes 0. And likewise, when we do something similar, and this term here, we integrate this term out with the mu d mu. Again, the same thing happens. You get it dropping out to 0. So yeah, it essentially simplifies the equation a lot. So this essentially simplifies this equation a lot, and we are left with these two differential equations. Now this is actually 3 equation with 2 unknowns. Okay, 3 equations with 2 unknowns. Now you have I2, I1, the second and first moment, and I0 which is a 0th moment. So yeah, you have 2 equations, 3 unknowns. How do we get our last equation? We need to make an assumption, and we can assume our radiation intensity so-called to be isotropic, or in other words, 2 flux. So this is also known as the two-flux model. Yeah, this is known as the two-flux model. So the idea is this. The idea is this. So let's say we have a plane again, and then we have some point that we are considering here. Okay, and this one in this positive direction, here. Okay, we call this mu greater than 1, and then this one is mu less than 0. Okay, it's not mu greater than 1, it's usually mu greater than 0. So mu is positive here when we are so-called pointing in the forward direction. Mu is negative in the negative direction. So actually we can make this assumption that as long as mu is more than 0, the radiation flux is the same. I is equal as long as mu is more than 0. So in this hemisphere, we will have the same radiation, and in the other hemisphere, you'll have similar idea where mu is less than 0. So for example, if this is a hot plate, for example, that's a hot plate and this is a cold plate, right? So you expect that the radiation from the hot to the cold plate is bigger than the cold to the hot plate, right? Because this is the cold side and this is the hot side, right? So we expect the radiation from the hot to the cold to be more than the radiation from the cold to the hot. So this is for 1D geometry only, and that's where our 2D flux model actually comes in. Okay, so that is two flux model basically, and I'll just stop for now. But this actually helps us to gain our third equation. Okay, so I'll stop now. I'll come back next time. Thanks for watching.